In the previous video, we talked about exponential growth. In this video, we are going to talk about exponential decay, which is exactly the opposite of exponential growth. Now, before we start talking about exponential decay, there is a term that we have to define and you have to understand it pretty well. We define the half-life of any material to be the time that it takes for the element or the substance to decay to another material, so the original one loses half of its original amount. Consider that you have a material which is, let's say, is represented by this rectangle. The half-life is the time that it takes it loses half of its original amount. Now, the amount which is lost is going to be changed to another element, and this is usually happening to radioactive material, and we are going to talk about it with an example later on in this video. Now, for example, one of these radioactive material is uranium-239, U-39, which has a half-life of about 2 years. This means that if we start, let's say, with 100 milligram of U-239, after 2 years, we are going to have only 50 milligram of the original one. Another 2 years is passed, this becomes 25 milligram. Another 2 years is passed, this becomes 12.5 and so forth. Now you may say, the first 2 years, what will happen to the 50 milligram that we lost? The U-239 changes to some other radioactive material. These are all examples of what we call exponential decay. Now we are going to talk about the definition of exponential decay, which is exactly like exponential growth, but instead of having, the ratio to be a number greater than 1, now we have a ratio between 0 and 1. We define an exponential decay as a pattern of decay in which every term is multiplied by a constant fraction now, which is going to be between 0 and 1. So every term, you are going to multiply the previous term by a number between 0 and 1. This represents a exponential decay. As an example, consider a table of values like x, y. When x is 0, y is 1. When x is 1, y is half. When x 2, y is 1 over 4. When x is 3, y is 1 over 8. When x is 4, y is 1 over 16. You can see that the ratio of 1 over 2 over 1 is 1 over 2. 1 over 4 over 1 over 2 is 1 over 2. 1 over 8 over 1 over 2, 1 over 4 is 1 over 2. 1 over 16 over 1 over 8 is 1 over 2. You can see that the ratios here are a number between 0 and 1. This represents an exponential decay. Now, if we go ahead and plot an exponential decay function, the graph that you get looks like this graph. And if you go from left to right, you can see that the rate of change is decreasing. The reason is that at the extreme left, your tangent is going to have a slope which is between 0 and 1. When you go closer and closer to the right, you will see that your tangent is becoming parallel to x-axis, which is 0. So this means that your rate of change is decreasing. As in previous topic that we talked about exponential growth, exponential decay, they have their finite differences, meaning first difference, second difference, and so forth. They have a pattern which repeats. If you find the ratio of successive finite differences, you will see that that ratio is a number between 0 and 1. In the first example, we have a radioactive material U-239 which decays, and it decays to another radioactive material called plutonium-239 Pu-239. In this example, we have a U-239 which has a half-life of 24 years. This means that every 24 years we lose half of the material or half of the substance, and they become Pu-239. We are supposed to find approximately how long it will take for a 50 milligram sample of U-239 to decay to 10% of its original amount. We know that first we are going to find an equation representing this case. We are going to say, let's say D represents the number of half-lives. D represents number of half-life, and M represents the amount of material left. When D is equal to 0, meaning there is no half-life gone, we are going to have 50 milligram. When one half-life is passed, so D equal to 1 represents number of half-lives. So if one half-life is gone, we will have 25 milligram. When two half-lives is passed, we will have 12.5, and so forth. We know that this is an exponential decay because the ratio is going to be 25 over 50, which is half. 12.5 divided by 25 is half. Since the ratios are the same, then this is an exponential decay. The equation representing this is going to be M is equal to AB exponent D. Now, when D is equal to 0, we know that M is 50. So M is 50 when D is 0. B exponent 0 is going to give us 1, so we get A. So this means that your equation becomes M is equal to 50 B exponent D. To find B, I'm going to pick another value from table of values. Let's say D equal to 1. Then we know when D is equal to 1, we have only 25 milligram. So we're going to have 25 is equal to 50 times B exponent 1, because D is 1. From here, I get B is 25 over 50, which is going to be 1 over 2. And if you look at the ratios here, B is really 1 over 2. So we didn't need to do this one. Just by looking at the ratio, we could write the equation. So the equation becomes M is equal to 50 half exponent D. Now we want to know how many years it takes for the sample to get 10% of its original amount. 10%, as we know, is 0.1. So 0.1 of original amount. Originally it was 50 milligram, and I have to solve this one for D. Automatically 50 goes with 50, so I will get half a D is equal to 0.1. Now this is not a linear equation, this is not a quadratic, this is an exponential equation. There are a couple of ways of solving for D. One method is divide and conquer, which is just guessing, and then depending on the value decide, is your guess high or low, and then divide the intervals in half and then approximately find D. Another method is to use a graphing technology and plot this function and also this line y equal 0.1 and then find point of intersection. But the best method is to use the logarithmic functions. So what I'm going to do is I'm going to find the log of both sides. So I'm going to say log of 0.1 is log of half is 0.5, so I can write 0.5 exponent d. But the property of the log function is that it's going to bring the exponent down. So I'm going to get d log 0.5. To find d, I'm going to divide by log 0.5. So from here, I'm going to get d is equal to log 0.1 divided by log 0.5. Now, if you use your calculator with a log function, you will get that this one is approximately 3.32. Now, this d, remember, it's the number of half-lives. It's not number of days. But we know one half-life is 24 years. So the number of days is going to be 24 times 3.32, which is approximately equal to 11.02 days. So it takes about 11 days so that the 50 milligram of U39 decays to 10% of its original. 10% of 50 is going to be 5 milligrams. So 45 milligram is going to be converted to Pu239.